Hello everyone, with another example related to forces. I have two blocks of mass m, small m, the hanging object, and the capital M are connected via pulley with the configuration as shown. The coefficient of static friction is us between the block and the surface, the capital M and the surface. What is the maximum mass of the capital M mass, or that big box on the inclined surface, so that no sliding down will occur? All right. The way to handle it, as a start, we will go with that the motion, it will be going downward. So that's anything going this way, it will be a positive acceleration. Now let's do the free body diagram on each object separately. That's the capital MG, and the component will be like this. It's mg cosine theta, and the one on the x component, or parallel to the inclined surface, mg sine theta, and here is the normal force, and I will have here the tension. It's important to remember the note that is no sliding, so anything will be resisting my motion to downward will be the static friction, and it will be going upward. Now here for the second object, or the small m, that's the tension, and I have here the mg, just the weight. Okay. Now let's see how we can handle these equations to find the value of the capital M. If I start with the object M, the big M, and following the formula of Newton's where it's equal ma, from this I can write this here. That's mg sine theta minus tension minus static friction force will equal capital M multiplied by the x. However, the question is saying no sliding, which means there is no motion on the x-axis. That term will be 0. Okay, I can kind of like keep it like this for now. Now let's go with the object small m, and again apply Newton's law where it's equal ma. From this one I can say, all right, it's t minus mg and equal ma. Again, no motion, no acceleration. This one will be equal 0. So in the equation system here, I can simply eliminate the tension because it is the same rope or the same cord have the same tension. They can cancel each other. And here I will end with this value. It's mg minus static friction minus mg, and this is all equal 0. I could write it like this: mg sine theta equal mg plus static friction for now. So I'll leave this equation here in this rectangle box, temporary, and we will get back to this one very, very soon. Now, I don't know how to find the value or the magnitude of the static friction as it is like this. So I will do this. I will go to the from y-axis. I can say the total forces on the y-axis equal capital MA. Again, there is no acceleration on the y-axis. Now, someone might ask, why am I going to the y-axis? Simply, we know that static friction equal mu s multiplied with the normal force, and the normal force, it's on the y-axis. So we have to go and find how much is that normal force. So let's go back to the y-axis. It's going to be normal force minus mg cosine theta equal 0. From here, that will give me what is the normal force. It's equal capital Mg cosine theta. Okay, great. Now I know how much is the normal force. I can multiply it with the static coefficient of the surface or static friction, then I can put it back on this equation where I have it in the rectangle box. Let's put them all together in a way we can read it. So here we go. This is the way to do it. So we said mg sine theta equal mg plus static friction. That's mg plus mu s fn. And one more time. This one was mg cosine theta. All this will equal mg sine theta. All right, and this one here is the static coefficients. Now let's put the capital M terms together. So it's going to be mg. I'll take it as a common factor, and it will be sine theta minus us cosine theta, and that will equal mg. Now one more time, I can eliminate the gravity acceleration, and from here I can find how much is m capital. It will be small m divided on sine theta minus s cosine theta. That's the value of the mass m to stop this system from sliding downward. Okay, I hope you find this video useful, and we'll see you again with other examples where there is numbers to be used. Thank you.